In the series Advanced Mathematics, we are going to start the next chapter. It is vector calculus. So this is lecture 1, and in this lecture we will talk about the basic concepts related to the differential calculus of vector valued functions. So first definition we have, it is scalar point function. We are saying a scalar point function, it is written as phi of x, y, z, is a function defined at each point in a certain domain D in a three-dimensional space. So we are saying phi is a function, it is defined from R cube, the three-dimensional space, to the real numbers. That is, to each point in the space we are assigning a number. So it is a real function and its value depends upon the location of the point P, X, Y, Z in D, and it does not depend upon any particular coordinate system. So either we are taking the Cartesian coordinate system, spherical polar coordinate system, cylindrical coordinate system, it does not depend upon this. So it is corresponding to this point P, we are saying the value is fixed, and this scalar point function defined on the domain D is called the scalar field in D. So this function is also called the field, scalar field. So if we talk about an example of this function, then the distance function we are saying, we are talking about phi of P, that is equal to distance of the point P from a fixed point Q, and the coordinates of the point Q, they are x1, y1, z1, and we are saying the value for this, it is square root of x minus x1 square plus y minus y1 square plus z minus z1 square. So phi is a scalar field, and in this case we are saying the domain D is the whole three-dimensional space. Now if we replace the coordinate systems, the distance will not change, the formula might change, but the value of the distance will not change. Value of distance, we are saying it will not change. So we are saying that the coordinates of P and Q will change, but the distance between P and Q will not change. Last we have is that the scalar point function, it may depend upon time t or some other parameter also. It is not necessary that it is always r cube over here. It may be r2, it may be r4. So if mathematically we are saying it may be, it is just a vector space over here, and the answer we are getting, it is from a field. The answers we are getting, it is from a field. Next definition we have, it is level surface. So we are saying let phi x, y, z be a single valued continuous scalar point function defined at every point P of a domain D. Then if we are saying that phi of x, y, z is equal to C for a surface, we are saying it is D, then it is called the level surface of the function phi. Suppose we are talking about that this is the point, say O, we are saying, and the temperature is being marked at different points around this point O. The temperature is being marked over here. If we are saying that at a distance of say 1 unit, temperature at all the points, it is T1. At a distance of say 2 units, the temperature at all the points, it is T2. At a distance of say 3 units, the temperature at all the points, it is T4. So we are saying what we are measuring? We are measuring the temperature at the point x, y and z, and we are saying that temperature x, y, z is equal to T1, and it is corresponding to this first circle we are saying, and this circle at which the points at which the temperature is constant, it is called the level surface corresponding to this function phi. This is one level surface. Corresponding to this temperature T2, we will have another level surface. Corresponding to this T4, we have another level surface. So we are saying that for different values of constant c, we will obtain different level surfaces. And further property we have is that no two different level surfaces intersect. So this is because we are saying if two level surfaces they intersect, it means at the point of intersection, the value of the scalar function phi, that will be constant c. So for both of these two surfaces the value is c, it means that they are corresponding to the same level surface. Next we have is if phi x y z, this represents the temperature at the point p x y z, then phi of x y z is equal to c represents the surface containing those points at all of which temperature is c. So this thing we have already seen, and these kind of surfaces, these are called the isothermal surfaces. So isothermal surfaces means we are saying we have, suppose this is some fixed point O, and corresponding to these points the temperature is fixed, it is c. So this surface we are getting, this is a level surface because at all the points the temperature is c, and this surface it is called the isothermal surface. It means that the temperature is constant, temperature is fixed at each point on this surface. Next definition we have is vector point function. So a vector point function, now it is important to note over here that we are talking about f vector. In the previous case we were talking about scalar function, so we were writing it is phi of x y z. Now we are talking about f vector xyz is a vector function defined at each point in a certain domain in the three-dimensional space. So when we were talking about phi, we have mentioned that phi is defined from R3 to R, that is, it is just a number. Now when we are talking about this function f vector xyz, we are saying its answer is basically again a vector. So this function we are talking about, it is defined from R3 to R3. So we are writing it is f1 x y z, then in the I direction, then f2 x y z in the j direction, and f3 x y z in the k direction. And this kind of function we are saying the vector point function f defined in a domain D is called the vector field in D. So for an example, it is being given over here that velocity at any point in a domain constitutes a vector field. It means we are talking about, if suppose we are considering the three-dimensional space, we are talking about any point over here, then we are talking about another point over here, we are talking about another point over here. At this first point we are saying the velocity is v1 and its direction is there. At this point the velocity is v2, its direction is different. At this point velocity is v3, its direction is different. So what we are saying that at each point this function is giving a value and it has also a vector quantity. Similarly, we are talking about angular velocity, gravitational force, electric force, magnetic force. These all constitute the vector fields. These all constitute the vector field, that is their answers are also the vector quantities. And the surfaces at which potentials of vector point functions remain same is called the equipotential surface. So we will see this definition in detail in our next slides, that what is equipotential surface in this case. Next is the vector fields of velocity of rotation and gravitational force. So suppose we are saying that any object is there, we are having this is the x-axis, y-axis and this is x-axis, y-axis and z-axis, and a body is rotating about the z-axis with an angular velocity omega vector is equal to omega times k vector. We are saying it is rotating about the z-axis, it is rotating about the z-axis and omega vector is equal to omega times k cap. Then the velocity of the object at any point p x y z at any instant t, it is given by omega vector cross r vector. So this is equal to omega k cap cross x I cap plus y j cap plus z k cap. So if we solve this cross product, the answer we get it is omega into minus y I cap plus x j cap, and this is the vector field which is shown in this figure. This will give us this is the vector quantity we are saying, this is a vector function, and this gives us the vector field. Similarly, talking about the gravitational force, we are saying suppose there is a particle A of mass m which is fixed at the point p naught. At this point p naught, we have a particle A whose mass is m, and a particle of mass m, we are saying another particle B is there and its mass is small m, it moves. Then by the Newton's law of gravitation, particle A attracts particle B by a force towards A, and the magnitude of the force is directly proportional to the product of the masses and inversely proportional to the distance between them. So we are saying the force exerted over here, F vector, that is minus G m into m over r square, and the direction of this force, it is given by r vector over r. Now why this negative sign is there? This negative sign represents that the force is acting towards p naught. So this gives us the field of force F vector for various positions of particle B. We are saying for this condition we are talking about, we have this r vector over r, and this r vector has the value, it is x I cap plus y j cap plus z k cap. It means that this force, the answer we are getting at corresponding to each point, that is a vector quantity. So this is a vector field. Next we have some parametric representation of curves and surfaces. So we are saying the position vector of any point on a 2 or 3 dimensional curve can be written as r vector. We are talking about the parametric representation. R vector t we are writing, it is x of t times I cap plus y of t times j cap, and we are saying that the value of t we have over here, it is a is less than equal to t is less than equal to b, where t we are saying it is some parameter. So if we are talking about a straight line in the first quadrant, we are saying the equation is x plus y is equal to 1. This is the Cartesian form. Now the parametric form of this equation will be t I cap plus 1 minus t j cap, where we are saying that the value of t is varying from 0 to 1. So these equations you should remember, these are the parametric form of certain equations. So first is the parametric form of the straight line. Second is circle x square plus y square is equal to a square. So the parametric form of the circle, it is given by a cos t I cap plus a sin t j cap. So we are saying if we substitute x is equal to a cos t and y is equal to a sin t in this equation, we will obtain this is a square cos t plus a square sin square t, that is equal to a square. It is satisfying this equation. So we are saying the parametric form of the circle, it is given by a cos t I cap plus a sin t j cap. So you should remember these parametric forms because they will be useful when we are solving certain problems. Next is the parametric forms of the ellipse. The Cartesian equation, it is x square over a square plus y square over b square is equal to 1. So the parametric form of this equation will be a cos t I cap plus b sin t j cap. What is being changed over here? When we are saying we are talking about the circle, it is a over here. Now it is both these values, these were a. Now it is a and b. So as the value of a and b will change, we will obtain the different ellipse. Next is the parametric equation of the parabola. So it is r vector t that is equal to a t square I cap plus 2a t j cap. The value of t in this case, it is varying from minus infinity to infinity, and a is greater than 0. So these are the parametric equation for straight line, circle, ellipse and parabola. Next we have is the circle in the three-dimensional space. So we are saying if we are talking about x square plus y square is equal to a square in three-dimensional space, it will represent a cylinder. We are taking its intersection with z is equal to d. So this whole will become a circle. Now the parametric equation of the circle in three-dimensional space, it is given by r vector t that is equal to a cos t I cap plus a sin t j cap, and the value of z is d, so it is plus d times k cap, where t is varying from 0 to 2 pi and a is greater than 0. Next we have is the circular helix. Circular helix means we have a circle and the value is changing in this way. So we have a particular definition for this using the curvature. We are not concerned about that definition right now. You can just understand that this is the circular, the shape in this way, it is the circular helix. We have made the separate slides and videos related to circular helix that you can refer using the curvatures. So the parametric equation we have, it is a cos t I cap plus a sin t j cap and c t k cap. And we are saying that this curve lies on the cylinder x square plus y square is equal to a square. So we are basically saying that we have a cylinder over here, and the equation of this cylinder, it is x square plus y square is equal to a square, and this circular helix, this basically means that we are moving like this on the surface of this cylinder. So the equation of this circular helix in parametric form is this, and it is lying on this cylinder. Similarly for the elliptic helix, we are saying over here both these values, this is a over here, a over here. Now if we change this a to b, we obtain the elliptic helix. So it is plus sign over, this is plus sign over. Now next we have is the parametric representation of surfaces. So we are saying a surface f x y z is equal to 0 can be represented in a parametric form by using two parameters, u and v. We are saying these are two independent parameters, and we are writing x is equal to x of uv and y is equal to y of uv and z is equal to z of u and v. These are the functions of u and v. So any surface f of x y z is equal to 0, it can be written in the form r of u comma v that is equal to x of u comma v I cap plus y of u comma v j cap plus z of u comma v k cap, where u and v, these are the belonging to the domain D. So we are saying if a surface is z is equal to h of xy, then its parametric representation is given by r of u v is equal to u of I cap plus v of j cap plus h of u v times k cap. So the first surface we are considering over here, it is the cylinder. We are saying it is x square plus y square is equal to a square. So in 2 dimensions, this is the equation of a circle, and the parametric form we have, it is a cos u I cap plus a sin u j cap. We are talking about this. If we are talking about 2-dimensional surface, we are saying its parametric form is given by this portion. Now we are saying it is a cylinder, it means that z is independent, that can vary anywhere. So we are writing plus v times k cap. So this surface, it is representing the cylinder, surface of the cylinder in 3 dimensions. Next is sphere. So for sphere, we are using the spherical polar coordinates. We have substituted x is equal to sin u cos v, y is equal to sin u sin v, and this value of z we have, it is a cos u, and over here we have it is I cap, j cap and k cap. Next is paraboloid of revolution. So we are saying z is equal to x square plus y square. So this is paraboloid of revolution. So we are having, for this portion we are having u cos v I cap plus u sin v j cap, because now this u is because this z is over here and we are writing over here it is u square. So to understand more about the parametric equation of the surfaces, you can refer the topic related to the surface of revolutions. So we are saying the parametric equation of a surface of revolution, it is given by f of u cos v, then f of u sin v and g of u. This is the parametric equation of surface of revolution, where f of u comma g of u, it is the parametric equation of the rotated curve. This is the parametric equation of the rotated curve. So we are talking about, if we are talking about the sphere, we are saying the rotated curve, it is circle. So in this case the answer we obtain, it is the parametric equation of circle we already know. So we are getting the value of f of u and the value of g of u. So when we substitute these values over here, we get the answer as it is a sin u comma a cos u. If you want to write it in the vector form, you can write it like a sin u I cap plus a cos u k cap. So this is the value of g of u and this is the value of f of u. So from this we are getting the value of the parametric equation of the sphere. So we are saying the surface of the sphere, it is two dimensional. That is why we have only two parameters over here. Similarly, we are talking about paraboloid of revolution. We are talking about that parabola is being rotated. So by using the equation of parabola and using this result, we will obtain the equation of the parametric equation of the paraboloid of revolution. Similarly, cone of revolution, z square is equal to x square plus y square. So we have in this case the answer, it is this. And the last we have ellipsoid. In ellipsoid we are saying the ellipse is being rotated. So when ellipse is being rotated, we have the parametric equation in this form. So we are basically using the result from the surfaces of revolution. So these are some standard parametric equations that you might need in solving the problems in this chapter. Next is limit continuity and differentiability of vector functions. So we are saying let the vector function is written in parametric form as this. So it is f vector t is a vector function and its components, they are written in parametric form f1 t I cap plus f2 t j cap plus f3 t k cap. Now if we are calculating the limit of this function, we are saying limit t tends to a, f vector t is equal to L vector if we have f of t is defined in some neighborhood of a. We are talking about this is the limit a. We are saying this f of t, it is defined in some neighborhood of a and corresponding to epsilon greater than 0, there exists delta such that mod of f vector t minus L vector is less than epsilon for all 0 is less than mod of t minus a is less than delta. So we are saying when t is close enough to is in the neighborhood of a, then f of t is in the neighborhood of L. Now the definition of continuity we have, it is f vector t is said to be continuous at t is equal to a if the value of this limit, we are saying limit t tends to a, f vector t that is equal to f vector a, and the function f dash t, it is this f vector t is said to be differentiable at t is equal to a if we are saying that the limit delta t tends to 0, f vector t plus delta t minus f vector t over delta t, this limit exists, then we write that this value is equal to f dash of t. So, this is the condition for differentiability of a vector function. This is the condition for differentiability of a vector function. And if we are talking about the parametric form, we are saying that the function we have, it is f vector t, that is equal to f1 t I cap plus f2 t j cap plus f3 t k cap. Then we are saying that the derivative of this function f dash t, that is equal to f1 dash t I cap. We are saying the derivative of the function is basically the derivative of the component functions. It is f3 dash t times k cap. So, this is how we can differentiate the vector functions when they are given in the parametric form. Next we have is the geometrical representation of r dash of t, the first derivative of rt, where rt is the position vector we are saying. So, suppose we are saying, we are talking about this situation over here, this is x axis, y axis and z axis, and we are saying that there is a point P over here, this is the point P over here, and Q is another point on the curve, this is the point Q, and we have, this is the curve we are saying, this is r vector t, this is the curve we are talking about. Now, the position vector of these points P and Q, we have the position vector of these points, this is r vector t, and the position vector of this point Q, it is r vector t plus delta t. Now, if we are calculating the value of delta r vector by delta t, the answer we are getting, it is r vector of t plus delta t minus r vector of t divided by delta t. Now, if this point Q is moving towards P, then we have, this thing implies us that delta t tends to 0. So, this value, this limit, this will become r vector t dash, this will become derivative, and the answer we are getting, it is limit delta t tends to 0, r vector t plus delta t minus r vector t divided by delta t. So, we are saying that this r dash t, this gives us basically the tangent to this curve at the point P. And if we want to calculate the direction of this tangent, we are saying the direction of the tangent at this point, it is given by r dash t over mod of r dash t. So, this derivative, the direction of this derivative will give us the direction of the tangent at the point P on this curve. Next we have is the higher order derivative and rules of differentiation. So, we have similar kind of rules as we are having for the scalar functions. We are saying if we have the function f of t given, it is f1 t I cap plus f2 t j cap plus f3 t k cap, and if we differentiate this function, we are differentiating it once, we are getting this answer that the components, these are being differentiated. When we differentiate it twice, we are saying that the components are being differentiated twice. Next we are saying we are having the sum of two functions and we are having the derivative of this. So, we are saying it is derivative of the sum of the two individual functions. Similarly, when we are talking about the product, it is f of t, this is a scalar function, it is being multiplied with the vector function and we are talking about the derivative. The answer we have, it is f dash t into f vector t plus f of t into f dash of, this is vector function of t. And similar is the case when we are talking about the dot product of the two vector functions or the cross product of the two vector functions. This is the dot product, this is the case of dot product, and this is the case for the cross product of the two vector functions. So we are saying that the general rules of differentiating the vectors are same as that of the real valued functions, but in case of vector product, the order must be maintained as the vector product is not commutative. So this thing you should remember, that you should not change the order of the product, because it is the cross product over here, so we cannot change the order of the product. Otherwise, most of the results they are same as they are in case of the real valued functions. Next is partial derivatives. So we are saying we have a function, it is r vector u comma v, that is equal to x of u comma v I cap plus y of u comma v j cap plus z of u comma v k cap. Now if we are calculating the partial derivative of r with respect to u, the answer we have it is limit delta u tends to 0, r vector u plus delta u v minus r vector of uv divided by delta u. And similarly, we are calculating for the partial derivative with respect to v, we will have over here, this term will be removed, we will have over delta v, and over here we will have it is delta v, and the limit we will have it is delta v. And similarly, we can calculate the higher order derivative. So these are the formulas for the partial derivatives of the vector functions. Next we have is the necessary and sufficient condition for f dash t to have a constant magnitude is that f vector t into derivative of f vector t is 0. So we are saying, suppose f vector t has constant magnitude, it has constant magnitude. So this thing is implied and implied by f vector t dot f vector t, that is equal to mod of f t square, and it is equal to a constant. Now if we differentiate this equation, this thing is implied and implied by f vector t into f vector t plus f vector t dot f dash t vector, this is equal to 0. So this thing is implied and implied by f vector t dot d by dt of f vector t is equal to 0, and this is the condition we are saying over here, that the necessary and sufficient condition for f vector t to be constant magnitude. It is important over here that we are talking about the constant magnitude. So when we are saying constant magnitude, so their dot product is equal to constant. Next is the necessary and sufficient condition for f dash t to have constant direction is the cross product of these two terms, it is 0 vector. So we are writing that f vector t, we can write it is equal to mod of f vector t into unit vector of f vector t, the direction of f vector t. Now if we differentiate this equation from both sides, we will obtain d by dt of f vector t, that is equal to mod of f vector t d by dt of f unit vector t plus f unit vector t into d by dt of mod of f vector t, because this is a scalar function. So we are not concerned about the commutative property over here. Now look at this term over here, we are saying if we take the cross product on both sides with f vector t, if we take the cross product on both sides with f vector t, then the second term will become 0. The second term will become 0 because f vector t, because this f vector t into f vector cross f vector t, this will be equal to 0. And what we are left with now is that f vector t cross d by dt of f vector t, that is equal to mod of f vector t square f cap t cross d by dt of f cap t, because this term again we can write it is mod of f vector t into unit vector of f. So this term comes over here and we get mod of f vector t whole square. So now we use this result to prove that this is the necessary and sufficient condition. So first part we are discussing over here, it is that the condition is necessary. So we are assuming that the function f dash t has a fixed direction. So what we are saying, that f cap t and f vector t have same direction. Both of these have the same direction. So what we get from this is that d by dt of f cap t, that is equal to 0. So if we substitute this value in the equation that we have derived, we obtain that f vector t cross d by dt of f vector t, it is equal to 0. Now in the second case we are saying we have to prove that the condition is sufficient. So we are starting with the result that f vector t cross d by dt of f vector t, this is equal to 0 vector. So we are saying that f unit vector of t cross d by dt of f unit vector of t, this is equal to 0. Also, when we are talking about f cap t, the mod of this is 1, which is a constant. So we are saying that f cap t dot d by dt of f cap t, this will be 0 because it is constant. Magnitude of this, both these is constant. So we are saying that this value is equal to 0. And what we obtain from this is that both of the above conditions are possible. We are saying both these conditions hold, that the cross product is 0, that the dot product is 0, and this thing is only possible if we have this term d by dt of f cap t, that is equal to 0. That is, f cap t is constant vector and hence the direction, this thing implies us f cap t is a constant vector, and this thing implies us that the direction of f cap t is fixed, and this is what we have to prove. Why? Because the direction of f cap t and the direction of f vector t, they are same. So this thing implies us that the direction of f vector t is fixed. The direction of f vector t is fixed direction, and this is what we have to prove in this result. Next we have certain problem based upon what we have studied till now. So the first question we have is that this function is given, it is v of t is equal to cos t plus t square into t I cap plus j cap plus 2 times k cap, and we have to calculate the derivative of this function. So derivative of this function will be v, this is vector quantity v dash t, that will be equal to minus of sin t plus 2t, derivative of this function. We are talking about the derivative of this first part, into t I cap plus j cap plus 2k cap, then it is plus cos t plus t square into the derivative of this second function. The derivative of this second function is I cap, and if we adjust the terms over here, we will obtain that v dash t, that is equal to cos t minus t sin t plus 3t square times I cap plus minus sin t plus 2t times j cap plus 2 into minus sin t plus 2t times k cap. Next function is Vt is equal to product of these two. So either you first multiply, take the dot product over here, you will obtain that V vector t, that is equal to 3t cube minus 10t cube plus 6t. So one thing is clear, that this is not a vector function, this is a scalar function. The answer, we have a scalar value over here. So we are not putting this vector sign over here, and when we differentiate this value, we get V dash t. We are not putting this vector sign over here. The answer we get, it is the normal differentiation. It is when you differentiate these values, you will obtain the answer you are getting over here. It is 6t minus 7t cube. So answer is 6 minus 21t square. So this is the derivative of this function. Third is the cross product of these two, and this is the vector function because it is cross product over here. So first we are calculating the cross product. So if we calculate the, or you can, what you can do is you can directly differentiate these functions. V dash t we are saying. So answer we have, it is I cap plus e raised to the power t j cap minus 2t k cap cross t square I cap plus j cap plus t cube times k cap. Then it is plus t I cap plus e raised to the power t j cap minus t square k cap cross, the derivative of this is 2t I cap plus 3t square k cap. Now if we do the product over here, the cross product of these two, and we do the cross product of these two, we obtain these two determinants. And on solving this, you can look at these calculations over here, and on solving this, you will obtain, this is the final answer in this case. That is the value of the derivative of this function, it is equal to this. Next is, if du vector by dt, that is equal to w vector cross u vector, and dv vector by dt, that is equal to w vector cross v vector, we have to prove that d by dt of u vector cross v vector is equal to this value. So this is equal to du vector by dt cross v vector plus u vector cross dv vector by dt, and we are writing what is du by dt. It is given to be w cross u vector cross v vector plus u vector cross w vector cross v vector. Now if we apply the formula for the scalar triple product, we will get, it is w vector dot v vector into u vector minus u vector dot v vector into w vector plus u vector dot v vector into w vector minus u vector dot w vector into v vector, and on solving all these values, you will obtain the final answer as w vector cross u vector cross v vector, and this is what we have to prove. This is what we have to prove in this case. Next is, if f vector t is a unit vector, prove that these two values, these are equal. So it is being given that f vector is a unit vector. So what we have is that f vector t dot f vector t, that is equal to 1. Now if we differentiate both the sides of this equation, we obtain f vector t dot d by dt of f vector t plus d by dt of f vector t dot f vector t, that is equal to 0. So this implies us that f vector t dot d by dt of f vector t is equal to 0. So this implies us that f vector t is perpendicular to f vector d by dt of f vector or either these two are perpendicular, or we are saying that the value of d by dt of f vector t is equal to 0. We have these two conditions, either of these two conditions will hold. So for the first case, we are saying when d by dt of f vector t is equal to 0, then we have mod of f vector t cross d by dt of f vector t, that is equal to 0. So we are saying that both these values, these are equal. And second case, we are saying when these two values, these are perpendicular to each other, and these values, these are perpendicular to each other. So what we have is f vector t cross d by dt of f vector t, that is equal to mod of f vector t, mod of d by dt of f vector t, and sine of pi by 2. Now sine of pi by 2, it is 1, and f vector t, we are saying mod of f vector t, it is equal to 1. It is given that this is a unit vector. So we are saying that the answer we have, it is mod of d by dt of f vector t, and this is what we have to prove. Next is the acceleration at any time t greater than equal to 0. It is given by this formula. If the velocity v and the displacement r are 0 at t is equal to 0, it is being given that a vector, that is equal to d by dt of v vector, that is equal to 12 cos t I cap minus 8 sin 2 t j cap plus 16 t k cap. So if we want to calculate the value of v vector, we will integrate this equation. To calculate the value of v, we are integrating this whole equation, and we are getting the answer. It is 6 sin 2 t I cap plus 4 cos 2 t j cap, and last we have it is plus 8 t square k cap, and the constant of integration will be there. It is c vector is the constant of integration. Now it is being given that at t is equal to 0, v is equal to 0, and r is equal to 0. So if we substitute this value over here, we will obtain the value of c vector is equal to minus 4 times j cap. These calculations you can see over here. When v is equal to 0 vector at t is equal to 0, we get the value of c vector is minus 4 times j cap. So this gives us that the value of v vector is equal to this. Now from this velocity vector, we can calculate the displacement vector by integrating it. We have integrated this equation, and by integrating we are obtaining another constant, say c1, and to find this constant c1, the value of this constant c1, we are using this second condition, that at r is equal to 0, t is equal to 0. So this gives us the value of c1 is 3 times I cap. So when we substitute this value of c1 in this equation, we obtain the final answer that r vector is equal to this. So this is the final answer. This is the r vector we are obtaining over here. This is the displacement vector. So we have to calculate the velocity vector and the time and the displacement vector. So we have integrated these equations, we have substituted the initial conditions, and we have obtained the value of the velocity vector and the displacement vector.